This is the continuation of the derivative. In part 1, the derivative used in differential calculus was explained, using the slope of a tangent and limits. As a way of an example, the derivative of the function of x cubed was figured out and found. In this lesson, 2 or more examples will be worked out to further explain how the derivative is calculated. The first example says that the function of x equals negative 3x squared plus 7x minus 10. By now you should know this is a quadratic that yields the parabola shown here. By finding the derivative of this function, we will be calculating an equation to help us find the slope at any point of the parabola. Again, using the equation for the derivative f prime of x, when the limit of h approaches 0, f of x plus h minus f of x over h. We substitute our parabola equation into it. Notice that every x in the equation gets the x plus h treatment and get negative 3 times x plus h squared plus 7 times x plus h minus 10. This takes care of the x plus h. We continue with the function of x by repeating the original equation. Negative 3x squared plus 7x minus 10. All of it over h. We now expand the binomial x plus h squared and get x squared plus 2xh plus h squared. The new trinomial gets multiplied by negative 3, and 7 gets multiplied by the x plus h, minus 10. If we now combine the second part of the numerator of the derivative with what we have expanded, by the way, notice that this trinomial gets multiplied by negative 1. We get a polynomial where we can cancel common terms. The 3x squared, the 7x, and the 10s get cancelled, leaving behind negative 3h squared minus 6hx plus 7h. All of it divided by h. We factor the common h out and cancel the h in the numerator with the h in the denominator. And finally, we simplify the derivative to negative 3h minus 6x plus 7. Like we have done in the past, we find the limit of the function as h reaches 0. And the derivative of the original function of x equals negative 3x squared plus 7x minus 10 is negative 6x plus 7. Which means that when x is 3, the slope is negative 6 times 3 plus 7 equals negative 11. And when x is 1, the slope is positive 1. And when x is 0, the slope is 7, and so on. The second example is the function of x equals the square root of x, which is represented by this curve. Notice that this function doesn't allow for negative values of x, so that x is greater than 0. Anyway, let's do our substitution into the derivative equation. The f prime of x when h approaches 0 is equal to the square root of x plus h minus the square root of x, all of it over h. We simplify the radicals by multiplying by 1. The 1 in this case is a rational expression that completes the difference of two squares and yields a numerator with no radicals, x plus h minus x, which is simplified further by eliminating the negative x and positive x. The denominator in this case becomes h times the positive part of the difference of two squares, square root of x plus h plus square root of x. Of course, we don't multiply the h because it is being cancelled with the h in the numerator anyway. We are left with 1 over the square root of x plus h plus the square root of x. We apply the zero limits to h now and add the two radical x's. The derivative of the function of x equals radical x is 1 over 2 radical x, which means that when x is 1, the slope is 1 over the square root of 1 times 2, or 1 over 2. And when x is 4, the slope is 1 over 2 times the square root of 4, or 1 over 4. And when x is 9, the slope is 1 over 2 times the square root of 9, or 1 over 6, and so on. Okay, so far in this and the previous lesson, we have found the derivative of the function of x equals x cubed. Also, the function of x equals negative 3x squared plus 7x minus 10. And finally, the function of x equals the square root of x. Here are the results for the derivatives for each. If we examine the equation for before and after, notice that we could have done the same by just making of the exponent of x a coefficient of x and reducing the exponent by 1. The exponent becomes the coefficient and reduce the exponent by 1. The same happens in the second example, except that because it has a coefficient other than 1, the exponent gets multiplied by the coefficient, and the exponent gets reduced by 1. Negative 3 times 2 is negative 6, and the exponent 2 becomes 1. Because the second example has 3 terms, each term has to be done. 7 times 1 is 7, and the exponent becomes 0 and x becomes 1. The x is dropped. In the case of a number like negative 10 that has no x, the term is dropped completely. It disappears because, theoretically, it has a 0 exponent that, when multiplied by negative 10, it turns the whole term into 0. Now, this manipulation of a function to get an easy derivative is how differential calculus works. And it is important because it has many uses in science, engineering, and business economics. This particular procedure of multiplying the exponent by the coefficient has a name. It is called the power rule. Specifically, the power rule says that for any real number n in an exponent, the derivative is nx to the n minus 1. The exponent is reduced by 1, and the new coefficient of x is the product of n and the original coefficient of x. There are other rules in differential calculus, which we will cover later. The third example requires a little imagination. Because in calculus we play with exponents, then the radical has to be represented in exponential form. However, everything else is done the same way. The exponent becomes the coefficient, and the exponent is reduced by 1. Now, reducing 1/2 by 1 turns the exponent into a negative 1/2. So the derivative is 1/2 x to the negative 1/2. But we don't have to stop here. Negative exponents should be written positive by finding the reciprocal. So the x goes south by a positive exponent, and we finish it up by writing the fractional exponent in radical form. The derivative of radical x is then 1 over 2 radical x. All 3 examples check using the power rule. In the next and last part of the derivative, all the rules for differential calculus will be presented, and more examples will be demonstrated.